Hi, Mrs. Greathouse here. Today we're going to talk about the nature of liquids. This is section 13.2 in your Prentice Hall Chemistry. Okay, in this picture we have hot lava. As lava, it's a liquid. It's going to roll down the volcano and destroy most of the living things in its way. When it cools off, it's going to become solid rock. This gives us a clue that temperature has something to do with liquids, and it's all about the forces in between the molecules and how they're related to temperature. Okay, we need a definition of fluids. Okay, any substance that can flow is considered a fluid. This makes both liquids and gases fluids. Okay, when we look at liquids, we need a model for them, just as we did for gases. Again, we are going to talk about the kinetic energy of the particles as we get going. Kinetic energy, remember its relationship with temperature, but that's going to bring about an interplay between the motions of the particles and their attraction to each other. Okay, this is also going to help determine their physical properties like boiling point and vapor pressure. Okay, a little bit of vocab for us. When a liquid turns to a gas or vapor, this is called vaporization. Okay, when this happens at the surface of a liquid that's not boiling, the process is called evaporation. Okay, so when liquid turns to gas and there's no heat involved in a boiling process, this is evaporation. Then condensation is the opposite. It's the cooling of that vapor or gas back into a liquid. If we look at evaporation in an open container, the molecules that are going to evaporate, liquid that's going to turn into a gas or vapor, okay, they can escape from the container, as shown here in a pond or in a container without a lid. However, if we're talking about a closed container, examples here, the terrarium that's covered with a glass top or a flask with a cork in it, the molecules are not going to escape during evaporation. They are going to collect on the inside of that container at the top, and we'll see that condensation, those small drops of water all around the top. Okay, they're going to condense back into a liquid. Okay, for these molecules to be able to escape the surface of the liquid during evaporation, they need a certain amount of kinetic energy to be able to escape. Okay, so when these molecules are getting ready to escape from the liquid because they have a certain kinetic energy, once they become a gas above that liquid, they're going to make a pressure on the surface of that liquid. Those vapor molecules above the liquid that are creating that pressure, okay, that pressure is called vapor pressure. Dynamic equilibrium is all about these evaporation, condensation happening at the same rate. For every molecule you have that evaporates, one is going to condense back into the liquid. Okay, this is called dynamic equilibrium. You're not going to get a change in the amount of your vapor, and you're not going to get a change in the amount of your liquid. It's all going to stay equal. It's changing, but it's equal. It's changing one molecule for one molecule. So when you're working in a closed system and you have this constant vapor pressure, vapor and liquid are going back and forth in equilibrium. Okay, in a closed container, when the amount of evaporation equals the rate of condensation, okay, you're gonna have a constant vapor pressure. That's going to stay the same, and you're going to have dynamic equilibrium. If we were to heat up that closed system, okay, if we increase the temperature, then we're going to increase the vapor pressure. Those molecules are going to move faster to go from the liquid state to the vapor or gaseous state, and that's going to make more pressure, increase the vapor pressure with the temperature. Okay, this table is in your book. You don't have to write it down or memorize it. This is showing us different vapor pressures at different temperature. Okay, what correlation do you see? We'll talk about that Friday in class. Okay, just like we have an instrument to measure atmospheric pressure, which was our barometer, we have an instrument to measure vapor pressure, and it's called a manometer. It works in a very similar way. We're measuring the change in mercury. We can see here that we have ethanol on ice at 0 degrees. The molecules are changing from liquid state to the vapor and putting the pressure on the mercury, causing a small change in the level of mercury here. But if we put the ethanol at room temperature, we have more molecules leaving the liquid, going into a vapor, putting more pressure on our mercury, so we get this bigger change in vapor pressure. Okay, what about boiling point? Okay, we think of like when we make pasta and we heat up the water and it's boiling with big bubbles. Okay, that's way beyond boiling point. Boiling point actually happens way before those big rolling, boiling bubbles are there. Okay, boiling point is the point at which the vapor pressure of a liquid is just equal to the external pressure on the liquid. It's when you're starting to see that steam on the surface of the water when you're making pasta. Okay, this happens because we're adding more temperature, we're adding more kinetic energy to get those liquid molecules to vaporize. Did you ever make a cake and notice on the box that there are different directions for baking that cake at a higher altitude? Okay, this is why. There's less atmospheric pressure there, so it takes less temperature to get to boiling point. Okay, so if you look at the boiling point at sea level, the vapor pressure has to be above 101.3 kilopascals to get to boiling. But on top of Mount Everest, the atmospheric pressure is only 34 kilopascals. So we don't need as much kinetic energy to get those molecules moving to be able to escape the liquid and turn into a vapor. So water is going to boil at 70 degrees Celsius, much cooler. What conclusion can you make from this then with the relationship between external pressure and boiling point. Okay, at a lower external pressure, the boiling point decreases. At a higher external pressure, the boiling point increases. Okay, so take a look at this graph about boiling point of different substances. We're looking at temperature versus vapor pressure. What conclusions can you make about that? Okay, jot down an idea and we'll talk about it in class. Okay, as you have probably figured out from what we've been talking about, the boiling point of liquids is going to differ depending on their vapor pressure and temperature. Therefore, in chemistry, we have to standardize so that all scientists are talking about the same boiling point. We call this standardized boiling point normal boiling point. And this is defined as the boiling point of a liquid at the atmospheric pressure of 101.3 kilopascals. Okay, so I hope that gave you a little more insight on liquids. We'll talk about it tomorrow in class some more. Be sure you write your summary and write down a question for me. Thanks for listening.